Hello everyone, I'm Chao from Guangzhou University, and today I'll be presenting our collaborative work on simplification is all you need against out-of-distribution overconfidence. Our study addresses a crucial challenge in deep learning, particularly in the context of neural networks and their behavior when encountering unknown data. Neural networks are typically trained under the closed-world assumption, that is, using ID data within a fixed environment. When test data aligns with the training distribution, performance is often excellent. However, once deployed in the real world, models inevitably encounter unseen, OD data, which can lead to significant safety risks. Given a DNN classifier trained on a specific training set, when inputting unknown OD samples, we expect the classifier to output uniform low-confidence predictions, but it is likely to output overconfident predictions. We call this phenomenon the problem of overconfidence in OD. Given a DNN classifier trained on a specific training set, when inputting unknown OD samples, we expect the classifier to output uniform low-confidence predictions, but it is likely to output overconfident predictions. We call this phenomenon the problem of overconfidence in OD. Existing methods often aim to detect OD samples during inference to improve AI system reliability. These approaches typically design detection scores to quantify differences between ID and OD samples, using thresholds for separation. Some further enhance score separability through techniques like weight sparsification or activation rectification. However, none of these methods fundamentally address the intrinsic overconfidence of neural networks. Our work establishes a novel connection between model complexity and the overconfidence problem in DNNs. Motivated by the observation that DNNs are inherently complex, often overparameterized systems, this excessive complexity can give rise to emergent behaviors, such as overconfidence on OD inputs. We show that reducing model complexity can mitigate this issue. As illustrated in the figure, we progressively alleviate OD overconfidence by 1. Reducing model capacity via knowledge distillation, and 2. Limiting nonlinearity through the removal of activation functions. Building on these insights, we investigated the effectiveness of the two strategies in mitigating OD overconfidence and proposed a practical guideline. First, we evaluated the impact of different knowledge distillation methods. As shown in the table, we applied 4 distinct distillation strategies. All of them consistently reduced the mean maximum confidence, MMC, and improved OROC and FBR 95, demonstrating that knowledge distillation effectively alleviates OD overconfidence. In addition, we explored how varying student model capacities affect OD overconfidence. Using knowledge distillation on CVPR 100 and ImageNet 100, our experiments show that moderately reducing model capacity effectively mitigates OD overconfidence. However, if the capacity is reduced too much, the model may fail to perform the classification task adequately, leading to degraded performance on both in-distribution accuracy and OD detection metrics. Nonlinearity in deep neural networks primarily arises from activation functions, such as ReLU and sigmoid. Given ReLU's widespread use, we focus on the effect of selectively removing ReLU operations. As shown in the table below, we evaluate how different removal ratios influence OD overconfidence. To guide this process, we introduce the negative response ratio, NRO, which measures the proportion of negative inputs to ReLU layers. A lower NRO indicates a smaller contribution to nonlinearity. Results show that removing a moderate number of ReLU operations effectively reduces OD overconfidence and improves detection performance. To determine which ReLU operations are most suitable for removal, we compare the effects of removing ReLU layers from shallow, middle, and deep parts of the network, as well as from layers with the lowest NRO values. As shown in the figure on the left, all strategies help reduce OD overconfidence, with the most significant improvement achieved by removing ReLU layers based on NRO guidance. We also analyze the impact of initiating ReLU removal at different stages of training. As shown in the figure on the right, the timing of removal has a moderate effect on overall performance. The best results are observed when ReLU removal begins mid-training, around epoch 40, striking a balance between model stability and effective nonlinearity reduction. Proposed model simplification pipeline is illustrated in the figure below. Given a complex teacher model with high capacity and nonlinearity, we use knowledge distillation to transfer information to a low-capacity student model. During distillation, ReLU operations are selectively replaced with leaky ReLU, and the negative slope is iteratively adjusted from 0 to 1, ultimately transforming ReLU into an identity function. We extensively validated the effectiveness and superiority of our model simplification strategy in mitigating OD overconfidence and enhancing OD detection. Beyond its standalone performance, our method can be seamlessly integrated with existing approaches to further boost results. Finally, ablation studies confirm the effectiveness and soundness of the proposed knowledge distillation and ReLU removal strategies. Thank you all for your attention. For more detailed information, please refer to our paper.